Hello everyone. Okay, so in this video I am going to talk about abstract trees. In the previous video I gave you an introduction to trees, trees in general, and today in this video I'm going to focus on the implementation of a data structure in a form of a tree. That's why I'm calling it abstract trees. So when we are talking about trees, tree is going to be a very general form. Every node can have any number of children, right? For example, A has 2 children, B has 2 children, H has 2, I has 3 children, M has 0 children. So they have different degrees. Remember, we define degree to be the number of children. So if I am going to implement such a data structure, I have to keep the link to the children somewhere, right? Remember when we implemented the linked list, we have a node, and inside each node there was a link, there was a reference that was referring to the next item in the linked list, right? This link was called next. Remember that? I mean, I have a slide here for you for recap. Look at this. It was this link, which was a reference to the next node in the linked list. The implementation of tree is going to be very similar to the linked list, but an extension of that. Instead of just having one link to the next item, which actually makes it a linked list, in the tree, I'm going to have, if for example this is your node, I'm actually drawing it from, in a bottom-up way to make it more clear. So from each node, you are going to have more than one reference, right? You are going to allow to have more than one reference, and this way you are going to create a tree. Here and here, something like this. Okay, so where I'm going to actually keep those references, let me actually show you some potential implementation for the tree. Very similar to the linked list, I need 2 classes. One class for nodes. You see that I have called it tree node. Very similar to the linked list that I called it that slist node. I am going to have some data field here that keep the information. It is exactly similar to the item here. You can see that the implementation is generic. It is any type here, and it was also any type here, right? I'm actually drawing too much. I don't want to make it so look more complicated. Okay, and in addition to the data that we wanted to store in each node, I am going to have some data, right? In addition to the data, I need some references to the children, okay? Those references that we wanted to actually keep. If I'm implementing a general tree, I don't know how many children I'm going to have. So either I need an array to keep those references, or I can also create a linked list, right? So I wanted to actually tell you that this is going to be a list. Whatever you are going to use, it is going to be a list. And I am calling it children. It is going to be a list of what? A list of some references that all of those references are, all of these actually references that you are going to keep is going to be of type tree node. And this rest of it is the syntax of Java that you are mentioning that tree node, and also you are writing that anytime. So if you compare it with the implementation of linked list, I was just keeping one link here, but in the tree, I am keeping a list of that references. Okay, and I'm calling that list children. This other data type that I have here, that I'm calling it parent, this is just arbitrary. You can have, for example, just think about it in this way, that in addition to have access to the children, for each child, I'm going to also have access to the parent as well. So for all of the childs, I have access to the parent as well. This link is arbitrary, very similar to when you had that linked list. Remember that it could be singly linked list or it could be doubly linked list, that for each node you also have access to the previous, not only the next node, also have access to the next node. This is something like that. Sometimes you might actually need to have access to the parent as well, but in many cases you don't need it. And basically in all of the implementation that I'm going to show you in this class, we never actually keep the parent, but I just wanted to tell you that you can keep the reference to the parent as well. Okay, so the rest of the implementation is going to be very similar to the linked list. I have a constructor for the node. You see I have passed some data. You put the data in that, the field data that I have. I also need to initialize the list of children, the list of those references for the children here, these references, right? How I'm going to actually initialize, because I created a list, but this is just here you just have a declaration of the list. I need to initialize it. I need to take some space for that. And here I am creating a linked list. You could create an array as well, but if you think about it, when you have a big array, something like this, just think about that. You don't know how many children you are going to have, right? So it is just like you are taking too much space for keeping an array for all the children, because you don't know how many children you are going to have in each node. So it is just like you are taking some fixed amount of space to keep the references for the children in all of these nodes, and this is waste of space, right? So it's just easier that instead of taking an array which is going to take a fixed amount of memory, it is better to use a linked list. So it's just the matter of implementation. This is more efficient. Now let's look at the class tree. Okay, in the class tree, very similar to the class of linked list, that we had a reference to the very first node in your the very first node of your linked list, which we call it head. Remember? So we are going to have exactly similar to this in your tree. We are going to keep a reference to the root node. And this is that reference. Okay, so this is the only actual reference that I need to keep. From the root, you can have access to all of the other nodes in the tree. Exactly similar to the linked list, that from the head, you can access to all other nodes in the linked list. You started from the head. Remember, you created a loop that just updated and go over all of the nodes one by one. Similar to that, we can actually access to all of the nodes in your tree by just having access to the root. The constructor for the linked list, I actually created two constructors. One of them is going to create an empty tree. Okay, no, it makes sense to you, right? Just exactly like a linked list, that I can have an empty linked list, that you don't have any node in your list, the list is empty. Here I can have a tree which is empty. So basically root is referring to null. I don't have even one single node. And this case is going to create a tree that has one node. I'm passing some information, some data, and it's just like it's going to create one node, and that is going to be the root node. Okay, so applications for the tree. In the previous video, I have shown you that how if you have a markup language, when you are parsing your XHTML, XML, HTML, all of those markup languages, if you have a document written in that language, when the browser, any actually parser read it, it will parse it and will create a tree. So tree structure is very useful whenever you have a parsing algorithm, you're parsing something. How we are implementing file system in an operating system. So it will be a tree that from the root you are going to have a couple of drives, a couple of directories, and inside each directory you are going to have some other folders, and you see that it is a form of a hierarchy actually that you have created. So how the computer, how the operating system will implement it, it will use a tree to implement file system. Later on in this course, I mean more close to the end of the course, I will teach you about a data structure which is called heap. It is a form of a tree which helps us to implement priority queues, the queues that allows us to remove the item based on their some priority that you define. This is not like a linear queue, the first in first out that we have discussed. This is very interesting data structure. And remember, we have talked about algebraic expressions and how we created a tree expression for that. For example, a simple expression like a plus b multiplied by c. This can be actually represented as a tree. Where all the leaf nodes are going to be operands and all the internal nodes are going to be operators. Okay, so using an expression tree, you can simply just distinguish between an expression like this one or an expression like this one. That this one is going to be something like, sorry. Okay, we maybe actually come back to the expression trees in your assignments. Okay, there are plenty of applications for trees. I just wanted to mention that. I think I have spent quite some time on that. So if you have a tree, it means that you are keeping your information in a form of a tree, right? You're keeping some items in a tree. So if you have those items, basically it means that at some point you might need to access to those items, right? You have your tree, you want it actually, so something like this, that A here, B, C, I don't know, D, E. At the end, you wanted to, for example, print them. You wanted to check if some specific node has a specific properties. You wanted to copy some of these items somewhere. If you are storing these items here, it means that you are going to access to them, right? You're going to do something over it. How we are going to do that? It is going to be called traversing the nodes in a tree. Again, this is some extension of traversing the nodes in a linked list, right? In a linked list, you have all the items, all your items that You had your items, stored them in a linked list, right? And if you wanted to actually copy them, if you want to look for some item, you're searching for some specific item. If you wanted to copy these items, you need to traverse over the nodes, right? So this concept of traversing over the nodes in a tree is similar to that. But the issue is that traversing over a linked list was very intuitive and easy, right? From this node, you started from this node and you go to the next node, you go to the next reference, you go to the next reference. When you have a tree, traversing over the nodes is not as intuitive as traversing over a linked list. You started from the root where you are going. Are you go to visit this one? So if you go here, from here you don't have access to C. From here you only have access to D and E. And so you can see that this is not as intuitive as the linked list. That's why I'm going to explain the algorithms that we have for tree traversal. So when we had that linked list, the cost of traversing over the nodes was linear, right? You have an item, you wanted to visit all of them. What is going to be the cost? Intuitively, we would say that it should be O of n. It should not be something like n square or something. It shouldn't be costly. If you have an item, I wanted to just traverse over all items, and I want the cost to be O of n. And in a linked list, it is very clear that the cost is O of n. I wanted to give you some examples, some algorithms that for the trees also we can traverse, we can check all the items in the tree, again in O of n. And this is very good, right? Although the structure of tree is way more complicated than a linked list, still we can write some algorithms that traverse and visit all of the nodes in a tree in O of n. So basically we have 4 different type of algorithms for tree traversal in general. Postorder and preorder, these are the 2 algorithms that I am going to explain now. Level order, or sometimes we call it birth first order, is something that visit the nodes in a birth first order. So if you have a tree like this, level order is going to visit this node first, this node and this node, then this node and this node, then this node, then this node, then this node. So the level order or birth first search, in fact, visit the nodes based on their distance from the root. So that's why root will be the first node to be visited, because the distance from root to root is 0. Then all the nodes at distance 1. So these are going to be the nodes, both of these nodes are going to be the nodes at distance 1 from the root, then the nodes at distance 2, then the nodes at distance 3, and so on. If there is more nodes, it's going to actually visit them. Okay, so I'm not going to discuss more about birth first order. This is something that we have explained when we talked about queue. It was one of the applications of the queue that using a queue data structure, we can implement a birth first traverse of the trees. And in order traversal, the last one is some algorithm which is specifically work on binary trees. Next video, I'm going to talk about binary trees, and I will explain the in order tree traversal. So let's now focus on preorder and postorder traversal. As the name actually tells us, preorder. In fact, this traversal is kind of a recursive approach, and the whole idea is that you are at a specific node in the tree, doesn't matter where, and from this node you have access the data inside the node, right? And you can also visit its children. So the idea of preorder is that you first visit the node itself. For example, you wanted to print. You first, whatever is the data inside the node itself, and then after that, you will visit its children. So then after you visit the node itself, then you visit all its children. Okay, and be careful. This idea is recursive. So whenever you went to one of its children, you have to apply the same rule. You first visit this node, then you visit its children. Okay, let me actually explain this pre-order traversal over an example. We run the pre-order traversal over this tree. So it means that at first you have basically you have a recursive function. You should think about it in this way. You have a recursive function and you wanted to run this recursive function over this tree. You pass it the root. So you first run it from the root. Remember, when you have a tree, the only node that you have access to it at first is the root node. Just like in the linked list that you have access to the head only. You don't have all of the references, all of the rest of the references. So you should start from the head, or here in the tree, you should start from the root. So if I wanted to actually write down some pseudocode for preorder, it will be something like this. Preorder, and you pass a node. So let's just I'm just writing down as it's a reference, okay? The node, for example, let's call it P. This is a pseudocode. This is not going to follow the exact syntax. And then, for example, something like this, print P dot data. Then you will call the same function. So for C, that C is going to refer to the child C in P dot children. You call the same function and you call it over all of the children's. Okay, so this is the pseudocode. Let me now run this pseudocode over this tree. When you call it first, the first time that you call it, let's just call this one root. Then it's just like you are calling preorder and you pass the root. What will happen? Let me use a different color. So just let's I'm going to exactly read the pseudocode and run it. So when you are at this line, you are going to print the data. So whatever is the data, you are passing it to the root. So you are at first in this node, right? You are going to print whatever you have here, the data A, right? And then for all of its children, it has two children, B and H. For all of them, you are going to call the preorder. So it's just like from here, you are going to call the preorder and pass B. So then you will be in node B. In node B, again, it's just like you are in this line, you print the data, whatever the data you have here, so it's going to be B, right? And then you are going to go over all of its children. So be careful, I'm not going to go back to H here. No, I am in B and I'm going to call the preorder over all of its children. This is a recursive function. Okay, so again from B, I'm going to call the preorder over all children one by one. The first children is going to be C. Again, in C, you are in this line, right? You print the data, whatever it is, and then you will call the preorder over all of its children. There is one child, so from C, it's just like you are going to go to D. In D, again, you will be in this line, right? So you print the data, and then you are going to call the preorder or over all of its children. There is no child for D, right? So it is exactly like you are here. There is no child. You are going to the end of the recursive function, and it is exactly like you are going back in the recursion, going back to this function call, the function call that has C as the node P. Okay, and in C there is no other child, right? C doesn't have any other child, so from C you are going actually back to the function call for B. In B there is still one more child, so again you will call the preorder over the next child, which is E. So the next value that will be printed will be E, and over E you are going to call the preorder over all of its children. So it will call it over F first, and F will be printed. There is no child for F, so the function call will terminate and go back to its parent. And in E there is still one more child. You go to G, G will be printed, and from G you go back to E. There is no other child in E, so you go back to B. And from B there is no other child, right? So it's just like the function call that you were in, which is on B, it's going back to the node A. And in A, now it's time to visit the next child. So you are going to call preorder over H. And in H, you print the data, right? Print the data first, and then call the preorder over all its children. First, you will call it over this one. In I, you first print the data, and then you will call the preorder over all its children. So in J, the data will be printed. There is no other child, so after printing, it will go back. It will print, there is no child, right? So it will go back to I. And in I, you are going to call it over the next child. So K will be printed. No child in K, so it's just like the function call go back in I. And in I again, you call it over the next child. L will be printed. From L, there is no other child. You go back to I, and you are done with all the children of I, so you go back to H. In H, there is still one more child. You call it over M. M will be printed, and from M, there is no child, so the function call go back. There is no other children for H. From H, you go back here, and it is done. A doesn't have any other child, so the whole preorder call will be finished, and the output will be look like this. So I have the full preorder here, and you can see that it's just following those function call and how it actually works. This blue dots that you can see, it's just telling you that where the process has been done over this node. So it first print A, then go to B. If I'm going to write down some more official code for the preorder. Okay, preorder is an idea. You can do any kind of pre-processing. But what I'm writing here is just about printing. Okay, I'm going to print the data. You might actually do some other stuff over the data. You may actually calculate something. You may pass some information and add all of them, but the simplest form is just the printing. So how I am writing the code for this one, this is exactly the code for that, the pseudocode that I wrote for you. It is, more syntactical form of it, that you run the code, and as you can see over the each node you are printing first, then you are calling the same function preorder over all of the children. Here is just a syntax of Java, that if you have an iterator, if you have a list, whatever is actually the type of a list, if a linked list, an array list, or any other actually collection which has an iterator property, you can iterate over all the elements using this syntax. Okay, so it's just a syntax of Java. It makes it easier. So if you don't know about this one, you may search online or come to the office hour and talk to me. It's not a big deal. It's just iterating over all the child. And over each child, I'm calling the print order. So this is, the rest is just the syntax that print preorder is a function defined. This print preorder is a function, is a method that has been defined over the class tree node. Okay, and this method print preorder is a method that has been defined in the class tree. Okay, so if you are going to call print preorder over a tree, you will call this function. This is a public method. You will call this method, and inside this method you will call print preorder over the root. And after that, basically this is the recursive function that will be actually executed. This is something that you call it from outside of your collection, and inside that the method from the tree node will be called, which is this method. Okay, that was preorder. Now we can actually have a look at postorder. Postorder is going to be very similar to preorder. The only difference is that in the preorder, we will process the data of the node, the current node that you are in first, and then visit the children. In the postorder, you are going to actually just reverse this. You will first visit the children, then do the process over the current node that you are in. Okay, let me just explain it over this example. Again, let's write down the pseudocode for this. It's going to be very similar to the preorder. Post order. You are going to pass some, for example, node P to that. What you are doing is you will first call the post order over the children, and then you process whatever you wanted to do with P. For example, print P dot data. So if you compare this one with this algorithm here, the only difference is that this loop that iterates over, let me just erase this here. The only difference between preorder and postorder in the recursive definition that you write is that either you process the node first or you call it over the children. So in the postorder, we will do the children first, and then we will actually process over the data. In the preorder, we will process the current data first, and then we will run it over the children. I mean, in terms of writing the code for that, they look completely similar, just changing the order. But because this is recursive, it's completely changing the behavior of the function. So let's call this one over. Let me use a different color. Okay, you call this post order over the root, right? And this is the root. What would happen is, okay, the function that the pseudocode tells me to go over the children and call the post order over all the children. So I'm at root. I don't do anything but calling the post order over the first child. The first child is B, and now I'm in B. In B, again, the first thing that you do is you run the post order over all the children. So in B, I am calling the post order over the first child. Now I am in C. Again, in C, I am calling the post order over all the children. There's just one child here, so you call it over D. And in D, let me just clean here. In D, again, you want to call the post order over all the children. There is no child in D, right? So this loop, there's nothing to be done in this loop. This loop won't iterate. Then you go to this line and you print the data here. So the first thing that will be printed in this tree is going to be D, unlike the preorder, right? And from the, after you are done with this line, the function call is done, right? So it's going back to, in fact, its parent. In C, there is no more child here. You are done with all the child. So you will call this line. You will print the data of the node, which is C, and you go back to its children. In B, it's just like you are here. Still, there is one more child to call the post order. So from B, you call the post order over E. In E, you are going to call the post order over all the children. And you reach to F. In F, there is no child here. This loop we won't iterate. You go and print the data. So F will be printed. Then you actually go back to E. There is still one more child. You call the post order over this child. In G, there is no children. So you directly just print G. You go back to its parent. In E, you are done with this loop, right? And so you are going to this line and print the data of the node. So E will be printed. And then you go back to B. In B, again, you are done with this loop. You will go to this part and print the data of the node, which is B. Okay, so you from B, you are done, right? You go back to its parent. You are in A, you can come back to the root, but still there is one child to call the post order over that. So you call the post order over H. In H, I'm going to call the post order over all the children. So it will be called over I first. In I, you call the post order over all the children. So you call it over J. In J, there is no child. So there is nothing to be iterated over in this loop. So you go to this line and print the data. So J will be printed. And then you go back to its parent. In I, you call the post order over the next child. So you call it over K. In K there is no child, so this loop won't iterate. You print whatever is the data, K will be printed. From K you go back to I, you call the post order over the next child, you go over L, there is no child for L, so the data for L will be printed, and from L you go back to I. So here we are done with this loop for I, then you go to this line and print the data, so I will be printed, and then you go back to its parent. You are done with this function call, the function call will go back. In H, there is still one more child. It's just like you are in this loop, you are done with one of the calls, you call it over the other node. So you call it over M, there is no child for M, it goes to this line, M will be printed, and from M you go back. Right, the function call will actually go back. It's just like for H, we are done with this loop. Then we go to this line, print the information, whatever is the data in this node, and then the function call will go back to its parent. So you are done with the loop here for this node. There is nothing, no other child, so this line will be executed for A. So A will be printed and everything will be finished, and so we are done with calling the post order over the root. Okay, and this is going to be the output, which is completely different than the previous. You see that this is preorder, this is post order. Both of them are recursive. The function looks very similar, but because this is recursive, it has a completely different behavior. If I'm going to show you the more formal definition, I mean syntactically, this is the print preorder. Again, I am going to have two methods. This is the recursive method, the main method, which is going to iterate recursively. This has been written over the class 3 node, and if you are going to call the print preorder over the class 3, you will call this method. This is the public method that will be called from outside, and you call it over the root. Okay, this is just the syntax. You call it over the root, and what would happen? You have again a loop and some printing. Remember, in the preorder, it was just the order of the loop and the print was changed. Here I am first visiting all the children, I'm calling the post order over all the children, then I will print. In preorder, just the order of these two lines would be changed. Okay, now that we are done with the we have explained the codes, I should actually analyze the time complexity of these preorder and post order functions, algorithms. Both of them actually are going to have the same time complexity. The only difference between them was just changing the order of the lines, but I mean how much computation you are doing, both of them are going to exactly do the same thing. And how I'm going to actually calculate the time complexity, the thing is, if you have a tree with n nodes, when you are calling this function, this method post or order or preorder over the tree, how many function calls you are going to have? You are going to have exactly equal function calls as the number of nodes that you have. You call it over the root, and from the root you are going to actually call over B, and from B you are going to call over C, and from C you are going to call over D. So as you can see, you would never call your function over a node more than once. So how many nodes I have in the tree? N nodes. So in total I'm going to have exactly n number of nodes, so n number of function calls, n function calls. Okay, when you are actually analyzing the recursive methods, because the process has been kind of hidden, you can see that you are not, when you are looking at this function, you are not seeing all of the computation that will be done here, right? Because it is recursive. You are calling the function over and over. So when you are analyzing a recursive function, you have to think about how many function calls in total you will have, and then compute the cost of each function call. So far we have learned that we are going to have n function calls equal to the number of nodes. And what I am doing in each node, I am just printing something, right? Except calling some other function call, except calling the function calls, I'm just printing. There is no loop, or I'm not really doing some, for example, a loop that takes linear time or something. All that I'm doing is just some printing, for example, and the rest of it is just calling the function calls. So I can claim that the cost of each function call is going to be constant. So that's it. I have n function calls. I am just doing constant amount of work in each one. So in total, it is going to be O of n or theta of n. Both are actually correct. And intuitively, if you think about it, you are just visiting each node, and in each node you are doing constant amount of work. The time complexity is going to be linear for both post order and pre-order. Both of them are the same. One interesting exercise that you can do here is try to, instead of whatever we wrote here was recursive, right? Try to write your pre-order or post-order algorithm without recursion. Okay, if you write it without recursion, you will need a stack. I will try to actually post the full algorithm. It is a very interesting exercise, and you will see that when you are writing it in a non-recursive way, you will see that exactly the time complexity is going to be the same. The time complexity is going to be just linear. I have written the full actual idea. It's not a complete code, but it is basically the code that you need to create a stack. You will start from the root, you push the root to the stack, and then in a while loop, until the stack is not empty. Always, you don't care, just remove an item, pop an item from the stack. Then what you are doing, if it is, for example, pre-order, you print the information of that node, print, and then you are going to just look at all of its children and push all of its children back to the stack. Okay, because of this push, you will see that when you are popping, for example, the first node, all of its children will be pushed, so still the stack will not be empty. If there is no child, so of course you are removing something, but because you are actually pushing, the stack will be, this loop will iterate still. Okay, and in this way, we can see that it will visit all the nodes, and for each of these iteration of the loop, you will do exactly constant amount of work, and the total time complexity is going to be linear. This algorithm is very similar to the algorithm that we discussed for BERT first search, BERT first traversal using queue. The difference between these two is that we use the queue. It was BERT first. If we are going to use a stack, it's going to be post order or pre-order. Okay, in addition to time complexity analysis, I would like to talk about space complexity. Space complexity means that how much space, how much more space you are going to use when you are running your code. So for example, if you are doing, you are searching an array, you are going to just probably have a couple of local variables, right? And searching over the array, so except the input array that you are searching over it, you are not using additional space, just constant amount of additional space. But for some algorithms, you might probably need to get more information. So if you have an item in the array, in your input array, and you need additional array to do some processing, you would say that the space complexity of your algorithm is going to be O of n, because I'm using another array, for example, of size n, or even if it is of size n divided by 2. I mean, the idea that asymptotic analysis is going to apply there as well. So even if you are using an array of size half, still the space complexity is going to be O of n. Or if you are using only two other arrays of the same size, still the space complexity is going to be O of n. So here it is interesting to actually check the space complexity for this algorithm as well. When you are thinking about the iterative version of the space complexity, you can see that if I have a tree, I am using a stack, and this stack is going to take some space. How much space you would need for the stack? It's going to be equal to the number of nodes that you will have in the stack at one moment. Okay, so if I have a tree like this, although there are 7 nodes, but if you think about it, at the same time, there always will be only 3 number of nodes in the stack, which this tree is going to be the height of your tree. So I'm going to claim that the space complexity for your algorithm is going to be O of theta of h multiplied by d. That d is going to be the degree, how many children, maximum number of child each node is going to have. This analysis is important for me because, I mean, I wanted to actually just tell you that, for example, when you are writing preorder, you are, for example, your function call from the root is going to call this one, and then it is going to call this one, then it is going to call this one. So as the height of the tree is growing, the number of function calls that will be in the stack frame will increase. Okay, so you will keep this function call, this function call, this function call, and this function call, all of them. So I just wanted to emphasize that the height of your tree is going to affect the time complexity. This is something that I will come back to it when we talk about binary trees. So here just keep it as, okay, the height of the trees are going to have to play an important role in the time complexity and also space complexity when we are working on trees. So I'm almost done with, all of these three traversals that we are going to talk, the preorder and postorder. But just one thing, preorder and postorder traversals, we discussed about a specific form of it with just printing the information, printing the data. But the idea is important, that you are doing some processing, you are doing some data processing over all of the nodes in your tree. So either you do that processing of the data before you call the same function over the children, or you do it after. So if you do it before, it is preorder. If you do it after, it is going to be post order. So there are plenty of applications for pre-order and post-order traversals when you have a collection, when you have a data in a form of a tree. In general, I can say that if you are going to pass some information to the children, so probably you are doing the processing of the data over the parent and then pass the information to the child. So it is going to be a kind of pre-order. But if you are doing some pre-processing, some processing over the data in each node, that you need the information coming from the children, it is going to be a post order, because you need to call it over all the children, get some information from the children, and do the processing over the that node. So I'm going to actually show you a couple of examples here that we do a specific calculation using pre-order or post-order. The first one that I'm going to check is calculating the height of a tree. Just assume that you have a tree, you don't know what is the height of that tree, you wanted to write a method that calculate the height for your tree. Remember what was the definition of height? Height of a tree is going to be the longest distance from the root node. The height for each node is going to be the longest distance from that node to a leaf node. So based on this definition, all the leaf nodes, the height of all leaf nodes are going to be 0, right? Because a leaf node is a leaf node. So the distance from that node to a leaf node is going to be 0. So the height of all leaf nodes is going to be 0. Then I can actually recursively give this definition for the rest of the nodes. For each node, the height is going to be the longest path to a leaf node. So if you are calculating the height for this node, it is going to be whatever is the height of all of my children, the maximum of that plus 1, because I am one level over my children, right? So for this node, the height of my child is, one of them is 0, the other one is 0. Maximum is going to be 0, so the height for this one is going to be maximum of the height of this child and this child plus 1. So the height for this node is going to be 1. You see, this is a completely recursive definition. Again, here I can say that the height of this node is going to be the whatever is the height of this child, whatever is the height of this child, maximum between them plus 1. So the height of this one is going to be 1. How about this one? If I know the height of this child and if I know the height of this child, both of them, I can calculate the height for this node, right? Whatever is the height of this child, whatever is the height of this child, maximum between them plus 1. Maximum is going to be 1 plus 1, the height of this node is going to be 2. Okay, so I am going to exactly write down this idea over the whole tree. You are going to calculate the height of the tree. The height of the tree is going to be the height of root node. Okay, so I am going to calculate the height of the root. To calculate the height of this node, I need the height of all of my children. Okay, the idea is similar, right? So I need to call the same function, calculate the height for this child first, then calculate the height for this child, get all of this information, get the maximum between them, add 1 to that, then you can calculate the height for this. So what kind of tree traversal this is? This is going to be exactly post order, because you are going to call the function over that recursive function that you have over all the children. Then after that, it's just like you are getting some information from all of your children. So I need to call it over all the children, get the information and do some processing and find the height for this one. So I need to calculate the height of this node first. Again, if I wanted to get the height of this node, I need to calculate the height of all its children first. So I need to call it over this node. Then over this node, I need to call the height over this node. I need to call the height over this node, call the height over this node, call the height over this node. When your function calls are going to stop, it's just like the base case of your recursive function is when you don't have any children, right? So if you don't have any children, you are not calling any function call, and the height is going to be 0. So you return 0. 0 will be returned to this. Then here you are going to call the function call over this node, the height of this node. To calculate the height of this node, you are going to calculate the height over this one. It will return 0, and then you are going to calculate the height over this one. This is also going to return 0. Maximum between 0 and 0 is 0. You add 1 to that, so the height of this node is going to be 1. And you are going to return that value to this node. So when you are here, you are done with calling the height over all the nodes. You know that the height of this node is 0, and the height of this node is 1. So the height for this node is going to be 2. And 2 will be returned to its parent. Then you will call the function call the height over this node. Again, over this node, you are going to call it over all its children. 0, 0 will be returned to this node. And then you are going to call it over this one. 0 will be returned to this node. 0, 0, maximum is going to be 0 plus 1. The height is going to be 1. And this is exactly what value you are going to return. You return 1 to this node. And in this node, I know the height of this side is 2. The height of this side is 1. Maximum is going to be 2. You add 1 to that. The height is going to be 3. And I'm going to return 3 to the previous, to its parent. Okay, so this is the whole idea. How I'm going to write the code for that, it's just exactly just explaining the pseudocode, and this is the complete, more syntactical code. This is the recursive function that I wrote. As you can see, again, we are going to call over all the children. You are going to call the same function height, this method. You are calling this method over all the children. And for each one, it's just like at the first, you are initializing h to 0. So if there is no child, you are returning h, which is 0. It is exactly what would happen for a leaf node, right? It's just like there is no child, so whatever is 0 will be returned. But if there is some child, you will call it. You will call the height over all of those child. And I'm getting actually just the maximum and plussing 1 to that as well. So if there are some child, you are going to call it over it, and you get the maximum between all of them. Plus 1 will be the height. And this is going to be the method that has been written over the class tree. As you can see, this is the recursive method that I have written over the class tree node. So when you are going to calculate the height of the tree, you will call the height over the root. Right? This is going to be the height of the whole tree. This is exactly, a form of a, sorry, let me actually clean this, all of this here. This is calculating the height, but which tree traversal is this one? This is going to be exactly postorder, because what I'm doing is that I need to call over all the children, then I can calculate the height for this node. So this is going to be a postorder traversal. Another example is, this is going to be actually more fun. Just assume that you are writing a function for an operating system. So you wanted, there are some command line in the terminal of all of the operating system, either if it is Windows or Linux based, whatever. There are some actually command lines that do the same process, that you, whatever is the file system that you have, it's going to actually print all the directories. But because this is command line, this is going to have a specific format. So if I have a file system in this way that it's going to be the root, in the root I have two directories. One, just assume one of them is called user, another directory is called var, and in user I have two other directories, bin and local. In var there are three directories. Okay, and at the end I'm going to print all the directories in a like a tree format, but it's going to be in the command line. How I'm going to do it? So the root is going to be first printed, and whenever you have some directories inside the root, you are going to just indent that. So you can see that I have one indentation. It's just like I'm printing one tab, and then I'm printing the name of the directory. So an inside user, I wanted to actually know that what are the directories here. So it's just like it is recursively show you all the directories. So inside user, there are two directories, bin and local. So to show that they are inside user, I need to put another indentation. So you can see that this is the indentation that I got from here. So it's showing that bin is going to be inside user, or local is going to be inside user. And then var is not inside user, right? This is directly inside the root. So there will be just one indentation. And in the var, I have three directories. So when I'm actually printing them, I will print enough indentation. Okay, so as you can see, this is a traversal of a tree. First, whatever is your file system is going to be represented using a tree, and I need to traverse, I need to see all of these directories because I'm going to print them. But in addition to printing them, I need some additional information. I need to print this indentation as well. How many indentation when I'm printing a node I need, right? Basically, the number of indentation is going to be the distance from the root. So when I am printing this directory, what is the distance from the root? The distance is 1. But if you wanted to actually, what is the distance from the root is going to be 1, right? So what is the distance from this one from the root? It is 2. But basically you can get a recursive definition for that. So the distance of this node from the root is exactly the distance of its parent plus 1, because this is just one level under this node, right? Whatever is the distance of this node will be plus 1, and it is going to be the distance of this node. So now you can see that when I am processing each node, I am getting some information from my parent. Okay, so you are passing some information, and you are actually doing that data processing over each node first, then passing some information to its children. So this is going to be a form of preorder traversal, right? You print the root first, then you actually are going to call it over all its children. And not only you are going to call, you are passing some information as well, that you are telling that, okay, the distance for me is 0, but get the distance of 1. So it's just like you are passing distance 1. And so it is telling the user to print how many indentation? 1 indentation. And then when you are in user, you print the name of the directory, and you pass some distance. You tell your children that, okay, your distance is 2. And in bin, when you are printing bin, you are printing 2 indentation before it. So this is going to be the full code. Just assume that this method is going to print the number of tab. I'm passing some number to that depth, so whatever is that depth is in fact the depth of the node as well, the distance from the root node. So if it is 2, it will print 2 tabs. If it is 1, it will print 1 tab. If it is 0, it doesn't print anything. Okay, so again, as you can see, this is a recursive method. you are printing the number of tabs that you want, you are printing the name of the directory, and then you are going to call the same method over all children. And when you are calling it over the children, you are passing whatever is the depth of myself. I'm going to add 1 to that and pass that information to the children. This is exactly what here you are doing, that when you are calling over the child, you are passing 1 to that, so where it knows that it should print 1 indentation, and where when call over its children, it will pass 2. It tells its child that, okay, print 2 indentation to all of its children. Okay, if there was more directories here, you would need to pass, for example, 3. Tell your child that, okay, your distance, your depth from the root is going to be 3. Another example, this is also fun. This is also about just assume you have a file system. You are going to write down a code, for a command line that calculate the space, how much space you are taking in some directory. The amount of space that you are going to actually take in one directory is going to be the amount of the number of, for example, files that you have directly in this directory, and the amount of space that your subdirectories are going to have, right? So something like this, that in the root, just assume that I have some couple of files that takes 7 kilobyte, and I also have some other subdirectories, right? I have some subdirectories, but I don't know how many files are there. So as you can see, you need to recursively just check the amount of space that you are taking in all of this. So I need to call calculating the space over this directory, and you are asking your directory to tell me how much space you are taking. And in this directory, just assume that inside that there are some files, so directly in user, and also there are some other directories. So user has some subdirectories, this one and this one. So you need to calculate the amount of space for all of the subdirectories, right? This is again a kind of tree traversal. You need to visit all of the nodes in your tree to calculate the space. But the way that I am processing here is completely different than the previous actual printing. Here I wanted to get some information from the children. So when you are calculating the full amount of space that you are taking in this directory, you need to know that how much space all of its subdirectories are going to take, add them all, plus the those files that you have, then it will be the space that you are taking in this node, right? So you need this information from this child that should be returned here, and you need this information to be returned here. So in user, how much space I'm taking? 12 plus 15 plus 4. So in total, it is going to be 31 kilobyte. Okay, so what kind of tree traversal this is? As you can see, I need to call over my child, get some information, then do the rest of processing. This is a kind of post-order traversal. I'm calling over the children first, then do the processing over the node itself. And even, the output that I wanted to have is going to be something like this, that I want to know the all of the subdirectories and the space that each one takes. So as you can see, the first thing that has been printed is in fact this node, right? So it is a post-order traversal. How to write a code for that? This is, more fancy. Not only you are calculating the space, you are also actually printing the directories in a tree form with the indentation. So I am passing some information and I'm actually getting some information as well. So as you can see, this method that we have written is going to actually pass some argument, that depth, that will help us to print nicely with enough indentation and tab. And not only that, it will return the amount of space that will you are actually going to take. Okay, so just this is, this is not an actual code. I just tried to write it in a syntactic form, but I don't really have a project that I have written this one. So just think about it. Just imagine that I have all a class and I have defined this method over that. So the method memory is going to calculate how much space you have directly in the, so how much file you have in this directory and how much space you are going to have, right? And then you are going to call it over all its children. So you pass the depth. Not only you pass the depth, you are going to get some information about how much space you are going to use, and then you will add all of these spaces. Okay, after you know what is the space, you are going to print the depth, so print the number of indentation that you have, then the name of the directory, then how much space you have. This is going to be exactly look like this, right? The number of indentation, the name of the directory, and how much space you have. How much space you are taking, including all of the subdirectories. So this is an example of, we would call this is an example of post order, because this is the main processing that you are doing and you need some information to get from your children. So you will call it over the children, and you process, you add all of those spaces, then print the space here. Okay, about, I'm done with this lecture. This is going to cover still chapter 18 of your textbook, but I have actually more examples here.